Alright, so in the last video we talked about the t-test. And if you remember going through chapter 6 there, we talked about the t-test and then we moved on to the z-test for proportions. And so we're going to have a very similar formula like we did last time, where we have the p hat is our sample proportion, so the x over n. P is the population proportion, and n is our sample size. And so we're going to use this whenever we're dealing with proportions. Alright, so let's look at an example here. So the first one that we're going to look at is obese young people. A researcher claims that based on the information obtained from the Centers for Disease Control and Prevention, 17% of young people ages 2 to 19 are obese. To test this claim, she randomly selects 200 people ages 2 to 19 and found that 42 were obese. At A equaling 0.05, is there enough evidence to reject the claim? So we have a couple things here. She's claiming that it's 17% of people. So we have our P equals 0.17, which is our claim also. That's what she's claiming. And then our alternate hypothesis is that it doesn't equal 0.017. Okay, so then we need to find the critical value. So here our alpha A equals 0.05. And then we see also that it's a two-tailed test. So we can find these critical values just from our z table. So it's a two-tailed test. Here we are, and we know that this area is 0.025 and this one is 0.025. Okay, so if we look up 0.025 on the z table, we should be able to get 1.96. Since it's symmetric, then that's why, when you look up 0.025 in the area, you get negative 1.96. And then since it's symmetric, that's how we get the other one. So this is negative 1.96, this is a positive 1.96, and the cat is walking on my keyboard right now. I don't know why cats always do that. Okay, alright, enough distractions here. So now we have to actually compute the z table for our test value. So we have our p hat. All we do is the x over n. We had 42 were obese out of the 200 people that were tested, so we get that that equals 0.21. Now we have the probability that she's looking for is 17%, so that translates to our p equaling 0.17. We can find q easily. You just do 1 minus the p, so we get 0.83. Alright, so now we have to make the decision. So we draw our normal curve here. Draw our normal curve. Looks real beautiful. Now our critical values were the 1.96 and the negative 1.96. And then we shade in the critical region. Shade in the critical region. We find that our z value that we had, did we ever find it? I don't think so. Let's actually compute it. It claims that it's 1.51. So here we go. Let's go back to this slide where all our variables are. So we're trying to find our z value. Remember that the z value for proportions, the proportions are whenever we had the hats. So it's the square root pq over n. There we go. P hat was 0.21. Subtract p, which is 0.17. Divide by the square root p 0.17, q 0.83. Divide by n, and that was our 200 people. All right, when you do that math, we get 1.51. And so that's our z-test value. We plot that in our normal curve, the 1.51, and we see that that's in the non-critical region. Okay, so there's not enough evidence to reject the claim. We see that it's in the non-critical region, so therefore we accept the null hypothesis. So, and if you remember, the null hypothesis was the claim. So there's not enough evidence to reject the claim that 70% of the young people ages 2 to 19 are obese. All right, so then we have another example. I'm going to go through that in detail in another YouTube video, but that'll be optional. All right, then after that, after we talked about proportions, we moved on to the chi-square distribution. And remember, we did the chi-square distribution. That was the third table that we had. And that was for when you were trying to find confidence intervals for the variance and the standard deviation. Okay, so if you remember, all the chi-squared values are greater than or equal to 0. They looked skewed to the right, positively skewed, like Squeaky's tail, who's sitting right next to me. And let's see, it's a family of curves, family of different curves. And for this, you got to remember too that the area under each curve is 1. So we have family of curves here. So here's another one. If I had another color, here's another one. Okay, so it depends on the degrees of freedom, and this is just a reminder of what was happening with that. So our third table was table G, and we're going to find if it's a right tail, left tail, and two-tailed. So different things need to happen. This is what I mean. So for this example, we're looking at table G again. We're doing the chi-square, so hone in on table G. 15 degrees of freedom, and we have our alpha is 0.05, and the test is right-tailed. So you draw a chi-square. There we are, it's right tail, so we know our area is 0.05, and that means the remaining area is 0.95. Now, the thing to remember, too, for table G is that instead of doing the area to the left, it tells you the area on the right. So, we just have to look up our 0.05, our 15 degrees of freedom, and we find our chi-squared value of 24.996. Please take a moment and verify that you can find that on your table. Now on the next example here, we got a left tail test. 10 degrees of freedom, alpha is 0.05. So we draw our nice picture. We got the area is 0.05, the area on the right is 0.95, and that's the value that we need to look up because our table tells us the area on the right. So we look that up. Our 0.95, 10 degrees of freedom, we get 3.940, which is our chi-square. Okay, so finally we're ready to figure out to use the chi-square test for variance and standard deviation. So here's our formula. It looks similar to everything that we've seen before. You see our n-1, which is the degrees of freedom. S is the standard deviation for the population. So S squared is the sample variance, and then sigma squared is the population variance. So all familiar variables here. So a couple of random things here. A sample must be randomly selected from the population. The population must be normally distributed for the variable under study, and the observations must be independent from one another. So the two-tailed test is a little bit more difficult here. We got our 22 degrees of freedom. Our alpha is 0.05. We're going to split the area into two. So we have our right tail is 0.025 area, and the left tail is the same. And so then we have to be a little bit more careful. We got our area in the middle is 0.95. That's not a problem. But when we look things up on the table, we have to be careful here. So you want to add up. So remember, to find this value, you had to add up the area on the right. So for our left value, we had to add up this plus this. And we get 0.975. And when you look that up in your table, you get 10.982. And when you look up this other value, we have 0.025. When you look that up, you get your value of 36.781. All right, so we get our two values that way. And then we're going to look at an example. However, I think I got